Imagine this. You are floating in the silent darkness of deep space. No sound, no wind, no up, no down. Just the cold, endless void. Until you see it. A shadow darker than anything you've ever known. A perfectly black circle surrounded by a halo of swirling, glowing light. A black hole. Your heart races. Every instinct in your body tells you to turn around, but you can't. Something about it is hypnotic, beautiful, and terrifying at the same time. What would really happen if you fell into a black hole? Not the movie version, not science fiction, the real physics. To find out, we have to start with what a black hole actually is. A black hole is not a solid object. There is no surface, no ground, no place to land. It is a region of space where gravity is so strong that nothing, not even light, can escape. Imagine taking a star with more mass than our sun and crushing it down smaller than a city, smaller than a mountain, smaller than a grain of sand. All that mass is still there. All that gravity is still there. But it has collapsed into something close to a mathematical point. We call this point the singularity. Around it lies the event horizon, the invisible boundary of no return. Outside the horizon, light and matter can still escape. Inside it, every possible path leads inward. You are still outside this boundary. For now, you are safe. You could fire your engines and fly away, but you don't. Instead, you turn off every thruster and let gravity decide your fate. You begin to fall. At first, the fall feels gentle. There is no air to rush past you, no ground to give you a sense of speed. You are just drifting, but faster every second. Gravity is accelerating you to thousands of kilometers per hour, then tens of thousands, and still you feel weightless. When everything falls together, nothing inside you feels pulled. Astronauts on the International Space Station feel the same thing. They are constantly falling toward Earth, but always missing it. You are doing the same thing here, just on a far more dangerous scale. As you get closer, something subtle begins to change. The pull of gravity at your feet is slightly stronger than the pull at your head. At first, it is tiny, far too small to notice. But with every kilometer you fall, the difference grows. Your body is being stretched lengthwise and squeezed from the sides. If you could look at yourself from the outside, you would see your shape becoming just a bit longer, just a bit thinner. This is the beginning of what physicists call spaghettification. But your attention is somewhere else. The view around you is becoming more and more unreal. The bright ring of the accretion disk spins around the black hole, made of gas and dust heated to incredible temperatures. Light does not travel in straight lines here. It bends, curves, and loops around the hole. You see distorted copies of distant stars, stretched arcs of light, a warped reflection of the universe itself. And ahead of you, the event horizon grows larger, like a black doorway in space. Once you cross it, no signal, no light, no message of any kind can ever return. You are falling toward the ultimate one-way border. Then, without any sound or flash, you cross the event horizon. There is no sudden impact, no invisible wall. Space simply continues, but its rules have changed. From your point of view, time still feels normal. Your heart is beating. You can move your arms. You can think. But the outside universe no longer sees you the same way. To a distant observer, your fall appears to slow down. The light leaving your body becomes redder and weaker. You seem to freeze right at the edge of the black hole, fading slowly out of view. For them, you never quite cross the horizon. For you, you have already passed it. Inside, all paths lead inward. It no longer makes sense to talk about turning around. Even if you could fire the most powerful engines ever built, every possible direction in space still bends toward the center. It is as if the river of space-time itself is flowing faster than you can swim, and the current is carrying you toward the singularity. The tidal forces grow stronger. The difference in gravity between your head and your feet is now enormous. Your body stretches into a long, thin shape, squeezed from the sides like an object being pressed through an invisible funnel. Eventually, even your atoms cannot hold together. Electrons are stripped away. Nuclei are torn apart. You are being transformed from a person into a stream of particles and energy, falling ever deeper into the heart of the black hole.
What happens next is where our current physics reaches its limit. According to Einstein's theory of general relativity, you must continue falling until you reach the singularity, a point of infinite density and zero volume. Space and time effectively swap roles. Moving forward in time is now the same thing as moving closer to the center. You cannot stop. You cannot hover. You cannot choose another path. The future for you is the singularity. But our other great theory of nature, quantum mechanics, does not like infinities. At the smallest scales, space and time may be grainy, discrete, made of tiny, indivisible units. Some physicists think that before you reach a true singularity, something else must happen. Perhaps the core of the black hole is not a point, but a tiny, incredibly dense ball of exotic quantum matter. Perhaps the information about everything that falls in is not destroyed, but somehow stored on the event horizon itself, like bits of data on a cosmic hologram. There are even bold ideas that black holes could connect to other regions of space-time, forming tunnels known as wormholes. In that picture, falling into a black hole might mean emerging somewhere else in the universe, or even in an entirely different universe. Right now, we simply do not know. No signal can escape from inside, so we cannot look in and check. What we do know is this. From the outside, a black hole shapes its galaxy. It bends light, steers stars, and powers jets that can stretch across hundreds of thousands of light years. From the inside, for anything that falls in, it is the end of a journey. A one-way trip into the most extreme place our laws of physics can describe. Black holes are not just monsters. They are laboratories of gravity, testing our deepest ideas about space, time, and reality itself. And the next time you look up at the night sky and see a patch of darkness between the stars, remember, somewhere out there, a silent, invisible giant may be waiting in the dark. Not to swallow the universe, but to remind us how small we are and how much of the cosmos we still have left to understand.